Okay, so I have this spring here, and it's 3 inches long and has a wire diameter of 0.0591 inches, and it's got an outside diameter of 0.667. So I think this is actually one that I own. I think this is the one that I pass around in class, or could have passed around in class if you guys were actually here. And so let me see, I measure it, and sure enough, this is the one that I got at like a Home Depot. It's got like 7. So and this to me is kind of an interesting thing. Let's see what happened. I get rid of the camera here. Why did I do that? I don't know. Maybe I'm just feeling like that. Let's go camera. All right, so here you go. It's a real spring. We will let's see, you got to be really careful when you measure the coils, right? That's 1.57 right there, thereabouts. But I measured it a couple different places, or just do it right, really close in there. And I think I also measured it this way, right here. So it's kind of hard when you get it in the curvature there to decide what the wire diameter is. All right, so I'm getting somewhere in the neighborhood of, there you go, that's actually 1.63. Let's see. Yeah, so okay, so now I can get that to be 1.45. It's hard to 1.47, and I just my thumb moved just a little bit. And then I can also get the so let's try to get the diameter of this, right? So it's hard to get the diameter like straight on, but you see I get like 17.13. Of course, I think it's reversed right now because of the camera. And then the length of this thing, it came out to be somewhere there about 77 or so I have right here. So maybe you believe me now, I don't know. I could also have looked this up, done this in metric here. I mean, done this in US units right there. So there you go. The important part here is that we have some dimensions off of a real spring. And we want to try to find some stuff out about it. That'd be kind of cool. I also wanted to measure this spring, right? I could put some weights on it and get rid of the deflections, but we don't have. I don't have my test rig for that yet. That was also on my list of things to do. I was going to 3D print a test rig. That's right, another 3D printing adventure. So what we're going to do here, we want to calculate the force to close this spring, and then try to carefully close it ourselves, and try to see if we believe what that amount of force is going to be able to do that. I did look this up in a so we can compare this to we can compare the results that we calculate from this to what's found in this catalog. And I took a look and I found an outside diameter of close to 17 right there, right? So I had 17.2, and maybe I think, well, that might be a good guy. And then I noticed that it was free length. That's cool. And then I also know his wire diameter. All right. And I counted the number of coils. So here is actually, this right above is a picture of the coils. So I will, because it ends right here, I'm going to count, that's going to be 1, 2, 3, you got to be careful, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 right there. Oops. And then this guy doesn't quite make him back over to there, right? So when I see 13 and a half, I kind of believe it. I think 13 and a half might be done, might do it. I decided when I calculated these that the total number of coils, when I first, the numbers I used 13, right? So we could have also used 13.5. And I also noticed that these ends are closed, right? So I decided this was a closed situation. And so the number of end coils was 2. Therefore, I said the number of active coils was 11 coils. That's often the first thing that we'll do. I'm going to use US units, even though I could use metric as well. So here's the diameter of the wire, here's the outside diameter, and here's the length. One of the first things I'll do is take the mean diameter by taking the outside diameter and subtracting out the wire diameter, or 0.618. Right? I'm going to need some material properties for this. So I go back over to here, and okay, so when I pick this out right here, you'll notice it says SPR is material. If I come back up here, SPR is spring steel. So what did I use? It looks like I might have used musical wire, maybe. Yeah, sure enough, I did. So I'm just decided that that's what I'm going to use. Why did I do it? I'm not even quite sure, to tell you the truth. But that's my exponent, and this is my A. I also used musical wire, and because this dimension is 0.059, 0.05, it's going to be in this range, I used a G of 11.85, and that's going to be M PSI. And then I also used music wire here, so I used 45. So these are some of the material properties that I decided to use. And but the one I care about first is going to be my G, 11.85 M PSI. And I think I might have backed into some of these in making that decision. So let's see. I think I have all the information I need to get my all-important A. We take the wire diameter to the fourth times the modulus of the modulus of rigidity divided by 8 divided by a big mean diameter cubed, and then number of coils, active coils. And I got 0.0591 fourth 11.85 E6 8. Big diameter is 0.618, the mean. And then I went to 11. And I found this to be 6.964 pounds per inch. And we want to compare that to, drum roll please, we got 7.1 pounds per inch. Right? So we're in the ballpark there. We made a couple decisions. This was a decision. We decided 11 instead of 11.5. There's some variation that we could have as part of this. Our goal here is to calculate the force to close the spring. So what we should do is figure out how much deflection is required to close the spring. So first off, that would mean, well, we know the open length, right? So this guy right here, here's LO. If we want to find the deflection to close, we take that LO and we take out the solid height, the solid length. So let's calculate the solid length. We find the equation we want to use for the solid length because it's closed, right? We want to use the wire diameter times the number of total number of coils plus 1. It's what we predict the solid length is going to be. So I could put that anywhere, but I'll put it right here. S, and we say that's going to be D NT plus 1. So we get 0.0591, and then it's going to be 13 plus 1, and I get for that 0.7042 inches, right? So that's just going to be 3 minus 0.7042. And did I find that value? I did. 2.291 inches. That means that we have to press. That's how much deflection is going to take. And we could actually check this. Let's keep it this time. we could actually check it with this, right? We got to be careful that it doesn't go flying. And I probably need a friend or somebody to come over here, and if I had a friend, to measure what that is. But that could be 3/4 of an inch. Sure, I'll buy that. And that's what we set up here. The solid length was 0.7. So moving on, we can now find what the force to close is going to be equal to the K times the del to close. And so that's going to be our 6.964 times our 2.291, and what we're left with is a force to close of words 15.95 pounds. So I had to use, my fingers had to press 16 pounds basically to get this thing to close. Now let's look at the maximum suggested load they have up here is 12. So they don't want you to go to its solid length. By the way, they also have the solid length is predicted to be a little bit larger than what they're saying up here. So of course, a lot of that has to do with the number of coils. Right, and they're saying that the ends are closed. I really think this is that spring. It could just be the variation in the way I've measured things, that I didn't get the exact numbers. But it could just be the batch, man. They could not everything is exactly the same, as it coming out of the factory. These are cheap springs. I bought like 4 of them in a pack for less than a couple bucks. I don't even remember. It might not have even been $1. So this is like really cheap springs, so you're not going to get like really good repeatability here. So let's see. Carefully close. Just check this value yourself. But I also have another one here. I'm going to estimate the safety factor at closure for a simple for the sample spring. All right. So let's continue on with this problem, and we're going to need to have the stress and the strength. For the stress, we're going to need to find the Bergstrasser, and to be able to do that, we need to have the spring index. So that's going to be the 0.618 divided by our 0.0591, and we get 10.46 is our index. And so the Bergstrasser is 4C plus 2. By the way, the index is usually somewhere between 4 and 12, so we're on the kind of the high side. And then we have 4C minus 3, right? So if we plug that C in there, we get 1.129, which is a pretty low number. We expect it to be something greater than 1. If we were to go back to that one page where we have the comparison right here, we could see, yeah, we're up there, so we're going to be kind of low, right? So we expect it to be somewhere between 4 and 12 as part of that, right? So we don't expect that number to be much greater than 1.4, and here it's like somewhere between 1.1 and 1.2. So that's to be expected. And now we want to try to get the stress of the thing, and so the stress is going to be that Bergstrasser. In fact, I want to use another color because I'm entertained by colors. That's right. I didn't use green much. Okay, so tau is going to be Bergstrasser times 8 times F times D over pi D cubed. So we get 1.129 and then 8 and then 15.95 for the force. The diameter is 0.618. And pi is delicious and 0.0591. And so what we end up with is 137.3 KSI. That's a lot. Oh, by the way, no, I think it's fine. Yeah. That needs to be cubed. That's what it was. All right. I knew there was going to be somebody in there that I was missing. So now let's figure out what the strength is, right? Well, the ultimate strength we can get from A divided by the wire diameter raised to the exponent M. And so I said previously that we were going to use 201 and 0.145. So we go 201 divided by 0.0591 to the 0.145. And what we end up getting, and we got to make sure we were using the right units here, but I do believe what I end up getting is 300. Interesting, like nice even number. And then I want the shear yield. That's going to be, we decided that we're going to use the 0.45. And what we're left with there is 135 KSI. And then lastly, we want the safety factor, which is just going to be the shear yield divided by the shear. So 135 divided by 137.3, and we get 0.99. So it's really, really, really close. And if you try to close this thing down, of having permanent deformation. And that's the end of the video, right? So that's the example problem with real world implications. Trying to find out what is our limits of this thing we bought off the shelf, and we think we've identified. We were kind of like investigators right there. We think we identified the correct spring, and sure enough, we did. And what do we think about that? That's right. That's what we think. Discard all that nonsense.